Hello everyone, my name is Bhuvaneswar Sagar Chintala, and today I'm going to present on my project work in data analysis. So my project is concrete compressive strength prediction. So let's quickly dive into the objective of my project. So concrete is one of the most frequently used building materials throughout the construction. So the quality of the concrete is determined by the compressive strength. So this is basically measured by crushing the concrete cube or a cylinder until it starts cracking and crust. So the pressure at which the concrete cube or a cylinder starts crushing, and it makes a little bit of noises and crushes. So it is called the concrete compressive strength, and it is measured in megapascal units. So in order to measure the concrete compressive strength, the concrete cube or the concrete cylinder needs to be settled down at least for 28 days. So after 28 days, the concrete cube or cylinder is sent for testing to the lab. So our new approach is, with the help of the data science and machine learning technology, I have developed an application which allows the engineer to determine the strength of the concrete in just few seconds of time without sending the actual concrete cube to the lab for testing. So next, let's get into the problem statement of my project. So, accurate strength prediction. The compressive strength of a concrete is critical property that determines its structural variability. So, uh, traditional methods which involves like sending the concrete cube to the lab. So, which takes like so much of time, and the accuracy is very low. So, while accurate and time consuming and labor intensive, that is labor intensive, time consuming. It's like a huge process. So, coming to the complex relationship, the compressive strength is influenced by various factors such as cement content, water to cement ratio, age, and additives. These relationships are often nonlinear and complex, requiring advanced analytical methods for accurate modeling and reducing costs and time. Physical testing requires substantial time to get the strength of the concrete, and it takes so much of resources and expertise. There is need for a scalable and efficient predictive model to estimate compressive strength without the need of the actual labor doing the work by testing the concrete strength. And also the material optimization. Predictive models can assist engineering in optimizing material proportion for achieving desired strength, ensuring cost effectiveness while maintaining safety. And data driven decision making, leveraging machine learning techniques to analyze historical data, providing an opportunity to make informed decisions and enhance the quality control in concrete production. So with this modern approach and using the technology, so we can predict the strength of the concrete just by putting the values into the and collecting the data. So for my project, I have used the data set from the UCI machine learning repository. It's a free public data set. So I have provided the link over here. You can check it. And so in my data set, I have like 9 features. Uh, the 9 features are cement, blast furnace slag, fly ash, water, super plasticizer, coarse aggregate, fine aggregate, age, and concrete compressive strength. So the concrete compressive strength here, these are target variable, where the other variables are input variables that are independent variables. So here I have done some exploratory data analysis. So I found out that the 9 features are quantitative in nature, and and also the data does not have any missing values, so there is no need of data imputation for the missing values. And the shape of the data set is 1030 rows with 9 columns, as I've mentioned it in the earlier slide. So here is the distribution of the compressive strength. So most of the data points are clustered in between 30 to 40 megapascal of the strength. So we could see that this is a kind of a normal distribution with slightly skewed towards the right. As you can see, the tail behavior, lower compressive strengths below 10 megapixel and 10 megapascal, and higher strengths above 70 megapascal are less frequent. So we can find very less data points beyond 10 megapixels and 70 megapascals, indicating these are relatively rare occurrences. So I have split my data into training and testing set. 80% of the data contains training set, and the 20% of the data contains testing set. So basically, I have built linear regression models, as this is the as the data output label is continuous variable. So we need to use the regression models, and also I have used some other models as well. And these models are used to scale data obtained by scaling the features using the standard scaler. And I have used the tree models as well. These use the original data, that is like without scaling, as they are not affected by the feature scaling. Both the training and the testing data frames were these are further split into X train, X test, and Y train, Y test. Here are the data frames with X indicate independent feature, while those Y indicate the dependent or the target feature. This means that X will have the data without the compressive strength, and Y will contain only one column, that is compressive strength. So here I have plotted the correlation matrix. So if you could observe, we can see that age, cement, superplasticizer, and blast furnace slag are in positive correlation with the concrete compressive strength. This means that the more the age of the age, and more the cement, and more the plasticizer, and more the blast furnace, then the more the strength of the concrete. So they are positively correlated. And we can see that water, coarse aggregate, and fine aggregate are in negative correlation. This means that they are inversely proportional. And superplastics, as I said, we could see that having negative correlation to the water. So this means that it might be in positive correlation with the compressive strength a bit. So from this we this correlation map will help to figure out the features which are highly correlated with the target variable, and from that we can pick the variables which will contribute best towards our model building. So basically I have built four models. The four are here we can see that linear regression model, random forest regression model, support vector regression model, and gradient boosting regression model. Out of these four built models, we could see that random forest and gradient boosting regression outperform the others in terms of lower error and higher r2 square r square. So we can see that the linear regressor model and the support vector regressors have lesser R2 scores, whereas the random forest regressor and the gradient boosting regressor have higher R2 score, indicating that they are better performing. And when compared to random forest regressor with the gradient boosting regressor, we could see that the errors are a bit less for random forest regressor. So our key performance indicators are like so we can reduce the time and workload using this regression models. And also we have compared the R2 scores, and we have adjusted the R2 scores of the model on both training and testing data set. So comparison of the RMSE scores on both the models and testing will help to understand that which model has the more error, so that we can pick the best model which has a lesser error. So and also from the observations we could see that water to cement ratio is proportional to the strength of the concrete. So these ratio must be maintained in order to have the concrete at the best of its strength. Yeah, thank you so much. I enjoyed really working on this project as I have learned how this uh, construction data can be used in the machine learning so that we could make progress in construction. Yeah, thank you so much again.